Now let's talk about the t-test with independent samples. We're going to do the basketball experiment, but this time instead of one group that's tested before and after, we're going to divide our participants into two groups who have equal skill at free throws. Group A is going to do the visualization training, Group B is going to actually practice doing free throws. And then after training, we're going to measure how many free throws they can make out of 100. Our null hypothesis is again that there is no difference between the real practice and the visualization practice. Null, nothing, nada, zip. Another way of saying is that the mean number of successful free throws for Group A is the same as the mean number for Group B. And in math talk, that's x bar sub A equals x bar sub B. The formula for T is now a little bit more complicated. Actually, it looks a lot more complicated because there are two groups instead of one. But it's really not that much more difficult because it's taking into account the same main factors that we needed for the dependent samples. First and most important, we have the difference in the means. The bigger that difference is, the bigger the t-statistic is, and the more likely we are going to be to reject the null hypothesis. So here are two data sets with means of 20 and 40, but that really doesn't tell us much all by itself because we don't know how the scores are distributed. And because we don't know how the scores are distributed, we need to put in the standard deviations of both groups. That's in the denominator. And again, the smaller this combined standard deviation is, the bigger the t-statistic will be. The more consistent our results, the more likely it is that we'll be rejecting the null hypothesis. Here are the data sets with means of 20 and 40. Now if we have a standard deviation of 9, this part here shows one standard deviation above the mean, and this is one standard deviation below the mean of the red group. Notice that the possible amount of overlap here, so it's possible because one standard deviation is 34% of our distribution. It's quite possible that the means can be a lot closer than what our observed means of 20 and 40 are. If we have less standard deviation for both of them, if they both had a standard deviation of 4, here's the cutoff point of 34%, one standard deviation above the mean, and one standard deviation below the mean, and you notice there's no overlap. There's not much overlap until you get down into the very tail of the distributions. Again, we're balancing out both standard deviations because it's unlikely they're both going to be identical. Let's take a look at this one where I have a standard deviation of 2 for one group and a standard deviation of 6 for the other group. Here's the one standard deviation for the 2's, and here's one standard deviation for the 6's. And again, there's not a lot of overlap until I get down to the tails of both of them. So when I have these small standard deviations, it's pretty likely that this difference in means really is telling us something. And finally, I have the formula taking into the size of both groups into account. Again, the larger the sample size, the bigger the t-statistic is going to be. Because all other things being equal, a larger n leads us to a more reliable result, and that reliable is in quotes because reliability is a mathematical and statistical construct, and I'm using it in the informal, everyday sense of the word.